Hey everyone, today we're going to start our last unit, which is modern physics. So kind of a bunch of stuff about like particle physics, the atom, and stuff like that. For today we're going to go through the models of the atom, which should be reviewed from your chemistry course, from whichever year you took chemistry. And then we'll look at something called the electron volt, which is just a different unit of measurement for energy. If you're good with those two things, you'll be alright. Now we're going to start with models of the atom. You don't know a whole lot. You don't need to know a whole lot about it. It should be reviewed from chemistry, so I'm really gonna fly through this. And again, I'm not gonna ask too many questions about this. Once we're done with this, probably the electron volt's the big thing for today. So we're gonna run through models of the atom. That's J.J. Thomson, Ernest Rutherford, Niels Bohr. Will be good. So J.J. Thomson, basically what he does experiments with cathode rays, which is just a beam of electrons, and what he discovers about them is that they're made of electrons. Like, he just didn't know what they were. So basically what he did was he discovers the electron. And he tries to fit this in with this idea of an atom, which physicists were fairly confident like it is an idea or concept that exists. So he tries to fit an electron into an atom and figure out what it looks like. And he was a little off the mark, but he did his best. He proposes this plum pudding model, which is basically just a bunch of positive charges. So it's these guys. I'm sorry, a bunch of negative charges. Those are the electrons. And those negative charges are sort of inside of this cloud, this like cloud of positivity, and that's his idea for a model. It sounds kind of silly, right? Now given what we know. But think about it. He knows that the whole thing has to be neutral. He knows that there's these negative particles inside of it. So how do you balance those two things? Well, we've got these negative particles, and in order to neutralize the whole thing, we just give it like this positive sort of thing that encapsulates it. And that was his idea. Again, off the mark, but it's significant in that he discovers the electron, which is an important part of the behavior of atoms. Alright, Ernest Rutherford, famous for the gold foil experiment. Basically what he does is he shoots gold foil. So here we've got kind of an animation of it. He shoots a gold foil, which would be the strip across the middle of the circle. He shoots it with a beam of what's called alpha particles, which are basically little positive particles. It's actually just a nucleus of a helium atom. He shoots a bunch of positive particles at this gold foil, and he finds that, if you're looking at this sort of animation here, most of them go right through. And what that means is most of this, like this atom, this gold foil, that most of the space it occupies is just empty. Like, these particles can go right through it. So he says, oh, most of the, most of our atom is just empty space because it didn't hit anything. But there must be something like in the middle, and that is a nucleus. So he comes up with the idea that there is a positive nucleus in the middle that repels these positive particles that he shot at it. But most of it is just empty space around the nucleus. So that was what was significant about that. Again, since most of these particles go right through, we were saying that most of this gold foil is just empty space, with like a really dense sort of positive nucleus in the middle. Which brings us to Niels Bohr. We're going to spend the most time with his model, so there's a little bit more to this. So, his contribution to the atomic model, he comes up with the idea that electrons orbit the nucleus. So we know that we have a positive nucleus in the middle, and that electrons are in the space around it. He says that they orbit at very specific energies. So you can have a couple of different orbits, like the one, like this picture that you're looking at right here. We've got two different orbits that this electron can have. One's like further out, and the other's closer in. And what's important about his idea for these two different orbits is that they have different energies. So you can have a low energy or a high energy. You may remember the terms like ground state and excited state from chemistry. And electrons aren't just trapped in their specific orbit or their specific energies. They can transition between them, so they can jump up in energy or jump down in energy, which is exactly what you're looking at in this picture right here. You can see the electron, it's at the top energy, so it can jump down, and then it can jump back up. So it's transitioning. Now the way it transitions is by absorbing or releasing energy in the form of light. So to go up in energy, this electron will absorb light, and to go down in energy, the energy will release light. This is kind of a jump from previous, our previous understanding of an atom. But it turns out that it's like a great match for experimental evidence. So we have these things called atomic emission spectra, so emission and absorption spectra. So again, this energy transition happens when light is absorbed or emitted. And the reason we know that this is a really good model is that when you do the math and you calculate this light that gets absorbed or emitted, they very nicely match the light patterns emitted by the elements. So like hydrogen has these very specific energies that electrons can orbit, and we're going to sort of dive into that later in this unit. And it turns out that like when you do the math for those energies and you have this electron jump up and down and up and down, those energies that it releases or absorbs like very nicely match what actually happens. So like the math that we do matches the experiments that we do, so we know that this fits together nicely and it's a thing that works. You may have seen this in, again, your chemistry class. So we have this this atom. It's got an electron orbiting a nucleus. And notice that this like squiggle yellow thing that keeps jumping in and out, that's the light. So notice that it releases the light or shoots it out when the electron goes down. And then it absorbs light when the electron jumps up. And those specific energies, you should remember from our unit on electromagnetic waves, match specific frequencies. Those frequencies match specific colors. So if you take like hydrogen, which is what Niels Bohr did a lot of his math on and work on, because it's the sort of the simplest atom that we can work with. He notices that if you can force it to release light, it only releases certain colors. Here you're looking at like a couple shades of like bluish violet. We've got like a red over here. And when he does the math, he's predicting that it will release just those frequencies, just those energies. And again, his math matches the experiments. In the same way, when the electron jumps up in energy, it absorbs light, and only those frequencies. Again, the frequencies that match the energies. So you can see that this emission spectra, which is just light that is released in these transitions, matches the absorption spectra, light that is absorbed in these transitions, depending on if the electron is going up in energy or down in energy. That was kind of a lot. It was kind of like the rough introduction to this, but we'll work with the math and this idea kind of a lot in this unit. So if it doesn't make a whole lot of sense right now, that's okay. We're going to keep building on this idea. But first we need a better way to define our energies, the energies of these photons. So let's just do a quick problem that'll remind us what we did and how we can calculate these energies, and then we'll look at a different way of measuring that energies, something called the electron volt. So as a quick review for calculating the energies of this light, which you may have picked up on, that's something we're going to deal with a bunch. Let's try number one together. A photon of light with a frequency of 6 times 10 to the 14 hertz is emitted from a light source. So we got a frequency. What color is this light? Well, the reason I'd expect you to know that is it's in your reference tables. If we go to this page, the electromagnetic spectrum page, here we've got our frequencies, and here are all over different colors. I said, what was it? 6 times 10 to the 14 hertz, which is, I think larger than this 5.2, but smaller than this 6.1. So I would call this color green. So if you were looking at light of this frequency, you would see green. So this would be a green colored object. Picture like a green neon sign, like a green light source. Alright, B, what is the energy of the photon in joules? So we can calculate the energy of this light as well, because again, we're really going to connect these different photons of light, these pieces of light, to their energies and the energy transitions of the electrons. So we've got to be able to calculate that. All right, the energy of a photon. We did learn an equation for that in the electromagnetic waves unit. If you forgot it, it's actually not in the wave section of your reference tables, it's in the modern physics section. It's this E photon equation, and there's two different versions. We've got HF and HC over lambda. I think the piece of information we have is the frequency. So let's use the one that's HF. E equals HF. Okay, H, what did H stand for? It stood for Planck's constant. Constants are in the front of the reference tables. Planck's constant, where do you go? There it is. It is 6.63 times 10 to the negative 34 joule seconds. Okay, and we're multiplying that by the frequency, which I think was given in the problem. 6 times 10 to the 14 hertz. Okay, multiply those two, I got 3.97. times 10 to the negative 19, I'm sorry, joules. Okay, and that's the energy of this light. So it's this photon, this tiny, 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 tiny little piece of light, this tiny particle of light, has this much energy. Great. What I'm hoping sticks out about this number is that it is not very big, which is good, because if every photon, if every little particle of light had a lot of energy, it would probably just beat you to death every time you turn on the lights in your room or something like that. This is very, very little energy. So it doesn't really make a lot of sense to measure it in joules, because it's just such a tiny number. It would be like measuring, the length of your finger in miles. Like, that doesn't make sense. It's not a good unit for that. So we do have a different unit that we use for energy. It is called the electron volt, abbreviated EV. So lowercase e, capital V. Kind of a weird name. What it means is, what its definition is, it's the amount of energy gained by one electron going through 1 volt. So imagine you have a 1 volt battery. Each individual electron that went through that 1 volt gains 1 electron volt, like 1 electron to 1 volt. If each electron went through 2 volts, it would gain 2 electron volts. If you send an electron through a 9 volt, it gains 9 electron volts. So that's where it comes from, kind of like the name suggests. Now this is a unit for energy, and what you're going to have to be able to do is convert back and forth between units. So basically, you'd have to be able to take, I don't know, let's say this number right here, 3.97 times 10 to the negative 19 joules, and turn it into electron volts, just a different unit for energy. To do that, you'll need a conversion. 1 electron volt is equal to, now you do have this in your reference tables, front page, somewhere. Here it is. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So that number's popping back up again from our electricity unit. So you're not going to get away from those conversions that we did. So if you had trouble with those before, let's take a moment to go over them. Let's start by... let's start by converting this earlier number, this 3.97, into electron volts. I know it's not one of the problems I asked you to do, but... So, the way we do these conversions is, I'm going to change colors for this. The way we do the conversions is this. We're going to start by just writing out the number that we had, which is the 3.97 times 10 to the negative 19 joules. And we're going to multiply it by some fraction, something over something, that will make joules go away. So we want this joules to go away and leave us with electron volts. Well, to make joules go away, I'm going to put joules on the bottom, because joules divided by joules cancels out. And I'll put EV on the top. According to the reference tables, 1 EV, so 1 electron volt, is equal to 1.6 times 10 to the negative 19 joules. Okay, just like when we did that electrostatics unit, I think we're dividing by the 1.6 because it's in the bottom of that fraction when we did this. So 3.97 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. Gives you 2.48. You may want to take a moment to try that in your calculator and make sure that you can get that as well. Just to make sure you're doing this right. So, 2.48 electron volts. I'm hoping you can see why we use this now. 2.48 is definitely an easier number to work with than this is, right? Because why would you call something times 10 to the negative 19 if you could just call it 2.48? Like, it's just so much easier to use. So that's why we use this electron volt. It's helpful for when you have tiny, tiny amounts of energy, like what we'll be talking about for this topic. So, if you're good with your conversions, I just want you to try 2, 3, and 4 on your own. So pause the video and give those a shot. If you're having trouble with the conversions, I'm going to go over number 2 right now, and then pause it after that, and then try like 3 and 4 on your own, and we'll go like that. So again, pause the video and try all these. Alright, a photon has an energy of 5 eV, so we're going to start by writing out our number. and we're gonna, again, do some kind of fraction here that's gonna leave us with joules. So I want EV to cancel out this time, a little different from before. Since I want electron volts to cancel out, I'm gonna put it on the bottom and put joules on top. And we know we did it right because EV on top, EV on bottom, those two cancel out. 1 EV, so 1 is the EV, goes with 1.6 times 10 to the negative 19 joules. Okay, looks like that 1.6 is on the top of the fraction, so we'll multiply them. 5 times 1.6 times 10 to the negative 19 gives you an answer of, I got 8 times 10 to the negative 19 joules. And again, that's a tiny amount of energy, which makes sense for like the smallest unit of light that you can imagine. So that's good. This is a good number. Again, notice that the 5 EV was definitely simpler to work with, which is why we use it. So this is our value in joules. For question 3, let's go the other way. A photon has an energy of, again, we're going to write out the number we're starting with, 7 times 10 to the negative 19 joules. And we're going to convert this into electron volts. So I want joules to cancel out now. If I want joules to cancel out, I'm going to put joules on the bottom and electron volts on the top. Alright, how many joules, how many electron volts? Well, I'm going to go 1 with the electron volts, because that's what our conversion says on the reference tables. And then down here, I've got that 1.6 times 10 to the negative 19 joules. Alright, okay, joules cancels, so we know we did that right. Joules on top, joules on bottom. Alright, we've got that 1.6 in the bottom of the fraction, and this looks like division. We're going to divide these two numbers. 7 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. Gives you a value of, I got 4.375 electron volts. Cool. So again, just a different unit of energy, just a different way of measuring it. I would like to point out now, I should have mentioned it earlier, you are allowed to have a decimal number of electron volts. This is not like when we did elementary charges during electrostatics, where I said you have to have a whole number. This is energy, which is a different thing, so you can have a decimal value for these. So this 4.375 is perfectly acceptable. Alright, number 4 is kind of like the complete problem. Here's all the different things I could ask you about this. So a photon with a wavelength of 1.5 times 10 to the negative 8 meters is emitted from a hydrogen atom. What kind of electromagnetic wave is it? When I say that, I mean, on our chart for reference tables, is it, gamma, X-ray, UV, infrared, micro, what is it? Well, it's got a wavelength of 1.5 times 10 to the negative 8 meters. That's a wavelength times 10 to the negative 8. Looking here. Okay, well, the wavelengths are on top, so it's these numbers. Times 10 to the negative 8 is here, which matches, looks like X-rays or ultraviolet. It's kind of like in that gray area in between. So I would take either one. So I'm just going to write X-ray. X-ray / UV. If you did this on your own and you wrote either one of those two, I would take it. They're both fine answers. Alright, what's the wave's energy in joules? Okay, so we have a wavelength and we want energy. Those are different things, right? We're not converting energy to energy. We're doing wavelength to energy. So maybe we need an equation for this. Let's check our photon energy equations, which were in that modern physics section. Alright, HF seems like a good idea, but I don't think we know the frequency, so this won't work. But maybe this HC over lambda would work. So see how that lambda means wavelength? H means Planck's constant, that's a constant, so we know that value. And C means the speed of light in a vacuum, which hopefully you remember from our electromagnetic waves unit is also a constant right here. 3 times 10 to the 8th meters per second. So we can plug all that in, and I think we'll be okay. It's just kind of annoying to write out, but it's not the end of the world. 6.63 times 10 to 34 joules seconds times 10 to the 8th meters per second, all divided by the wavelength, which is 1.5 times 10 to the negative 8 meters. Okay. So again, some calculator work here. And you get an energy of, remember, it's a photon, a single tiny, tiny, tiny particle of light. So we're not expecting a lot, a big number. And sure enough, I got 1.326 times 10 to the negative 17 joules. Times 10 to the negative 17 is like small number. So this makes sense. And we're good. Alright, wave's frequency. Okay. So there's a couple different ways we can do this. Let's go back. We're talking about photons. We can do E equals HF, because we know E now, right? We just found it, and we can set it equal to HF. I'm going to go back one, just because we haven't used the equation in a while, and do V equals F lambda. If you know the wavelength, you can always find the frequency. For V, remember, it's light, so it moves at the speed of light, 3 times 10 to the 8th meters per second. But again, if you did E equals HF, no problem with that. It's perfectly correct. And you should get the same answer as long as you're careful. But I'm just going to do this one, because I like it more. Basically why. Okay, 3 times 10 to the 8th meters per second equals, we're solving for frequency, and we know the wavelength from earlier. It's this 1.5 number up here. Cool. Divide the 1.5 across, and you get a frequency of, I got 2 times 10 to the 16. If you did it the other way, you may have got, rounded a little differently or whatever, but as long as you're in this neighborhood, you're good. If you're not sure if this made sense or not, go to the reference tables. We said it's like an X-ray UV neighborhood, and notice that in that X-ray UV neighborhood, we're at about times 10 to the 16, kind of in that neighborhood, so it seems like a reasonable number. Alright, what's the wave's energy in electron volts? Alright, we have the energy in joules now. It was this number up here. So we're going to convert that into electron volts. So we start by writing out the number that we're converting. That's a J for joules. Times, okay, I want joules to cancel out, right? So I'm going to put joules on the bottom. Okay, and we put EV up top. So I think 1 electron volt was equal to 1.6 times 10 to the negative 19 joules. If you forget that, well, you have it in your notes right now, or in your reference tables as well. Alright, 1.6 on the bottom, so let's divide. When you divide, I made a mistake, everyone. This was times 10 to the negative 17. But now when you divide, sorry about that, I got 82.875. Our energy in electron volts. Okay, so what we did today is we ran through the models of the atom. If you didn't get some of it, that's okay. Here's the important idea is the Bohr model. Electrons are in energies, and electrons can jump up in energy or fall down in energy by either absorbing light or releasing light. That energy can be measured in 2 different ways. In joules, which is what we've used all year long, or in electron volts, which is new here. And you convert it kind of the same way we did the elementary charge conversion. So as long as you can sort of perform that conversion, you're in good shape for today's lesson.